this lesson, we're gonna talk about helical springs. Now, a helical spring is a type of mechanical spring commonly used to store and release energy. Now, it consists of a coiled wire, typically made of steel, wound in a spiral shape. And so if we are to do this several times, adding more coils, by the way, this is considered a coil, we will now have this figure. Now, helical springs, when compressed or stretched, it exerts a force in the opposite direction, making it useful in various applications such as suspension systems, mattresses, and mechanical devices. Now let's take a closer look at the helical spring, and let's say that we'll apply a force P to one end right here, and then let's add a support at the top. Now doing that, we'll have this figure. Now let's try to make a cut anywhere along the spring, let's say right here. And so we'll consider this portion. Now if we'll analyze that part, it's helpful to transmit the load P to the center. And so we will now have this figure. Now let's try to make our free body diagram. But before anything else, let's first define the dimensions of the spring. Now this element is what we consider as the coil. Now first, we have the center to center distance between each coil, this distance. Now this is what we call the mean diameter or the spring diameter. Now, by contrast, the distance measured from the outer sides of the coil, which are right here and right here, that's what we call the outer spring diameter or the outside coil diameter, which we will define as d sub O. So this is the outside coil diameter. By the way, this is the mean coil diameter. Now next, we also have our wire diameter, which is this diameter. And then as labeled, its notation will be lowercase d. This is the wire diameter. Now for the purpose of derivation later, let's define half of the mean diameter as capital letter R. This is capital R, and then we'll call this the mean radius. These are our labels. And so now, let's try to define the forces acting on this wire. Now due to the force P, there will be a shear force that will develop on the wire, and then since this causes a clockwise twisting moment about the wire, then there will also be a torque developed or simply a twisting moment. And so let's now erase this, and then we'll now put the body in equilibrium. Now this shear force puts the body in equilibrium if we'll sum up forces along Y. And then since this force causes the wire to twist in a clockwise direction, let's say we'll apply this force, and then this is our moment arm, which is half of d or the mean radius. The twisting moment will be P multiplied by d over 2, which is a clockwise twisting moment. And so to resist that, we will have a resisting torque right here. Now note here that the moment is called a torque and not a bending moment because the direction of the moment is not coplanar to the cross section. And so let's try to make sense of the forces. Now if we'll sum up forces along Y, let's equate the upward forces and the downward forces. We have the shear force V, which is acting upward, that's equal to P. And so we have this equation. And then let's also try to sum up moments, and then we'll equate them to 0. And then let's assume that positive is clockwise. So summing up moments equal to 0, we have a negative torque or a negative twisting moment. That's why this is minus T. And then P multiplied by the moment arm going to the center of the wire, we now have P multiplied by D over 2. That's our twisting moment. And so moving this to another side, we have T equals P times D over 2, in which this is our twisting moment and this is our resisting moment. And then again, it is called torque because the direction of the movement is not coplanar to the cross section. This is what you have to remember because this will actually affect our resistance. Now let's move this to the side. And then let's try to define the shear stresses acting on this wire. Now first, we have the direct shear, which is caused by this force. This is parallel to the cross section. So we have, for the shear stress, the direct shear equal to force over area, or simply the shear force over the cross-sectional area. However, since twisting also occurs, then this element will also be subjected to torsional shearing stress. Now the formula for torsional shearing stress is TR over J, wherein T is the torque or twisting moment, which is usually in Newton meter or kNm or kips times foot. These are just the units of movement. Now in here, R is the maximum radius of the cross section. So if this is D, then we have small letter r to be this distance. This is the radius of the wire. And then J, recall in your statics that it is the polar moment of inertia. Or that's simply Ix plus Iy. Now Ix is the moment of inertia about the x-axis, and then Iy is the moment of inertia about the y-axis. Now sir, why are we using the polar moment of inertia? Now we are using this because twisting is resisted by both axes, x and y. Now recall that the unit of moment of inertia is mm to the fourth, or any dimensional unit to the power of 4. And then here at the top, because t is actually a moment, we have, let's say, Newton mm. And then r, since this is a dimensional unit, let's say that's mm, and then divided by j, which has a unit of mm to the fourth. We now have Newton mm squared over mm to the fourth. And so these will cancel, and then we are left with mm squared at the denominator. And so that's why this is a unit of stress, if we will just use unit analysis. Now let's try to combine these shear stresses, and then let's try to derive a formula that we can use later. So for our combined shear stress, we have tau equals the direct shear plus the torsional shearing stress. Now since we know that by equilibrium, V is just equal to P, we will just change V into P. That's why this is now P in our equation right here. And then we have TR over J. Now A right here is this area, or simply the area of the cross section. So that will be, if this is the diameter, the area will be pi d squared over 4. And then here we know that T is equal to P times D over 2. So this is P times D over 2, and then the radius here is this dimension, so this is lowercase d divided by 2, and then j will be ix plus iy. And so doing that, we have this equation. Now for circular sections, we actually have formulas for ix and iy. So let's say we have this section, and then let's assume a solid section. Our ix and iy will be equal to pi over 64 multiplied by d to the power of 4. And so we have ix and iy, and so our j will be ix plus iy, in which this is our ix and this is our iy. So adding both of these, since it contains d to the power of 4 in both terms, then we can just add the coefficients. So this is simply pi over 64 times d to the 4th multiplied by 2. And so 2 will cancel, and then we have pi over 32 times d to the 4th. This is where j comes from. And so substituting this part of the equation, we have p over pi d squared over 4 plus p times r times d over 2 over pi over 32 d to the 4th. Now by the way, d over 2 is just equal to r. That's why we are changing this. Now recall that this is our mean radius. And so notice here that d and d to the 4th will cancel. We will now be left with d cubed at the denominator. And so we have this. And also, we can actually isolate 1 over 32. And so if we'll make this 1 over 32, then we know that if we'll divide the numerator by a fraction, we can just multiply the reciprocal of this term to the numerator. Now, the reciprocal of 1 over 32 is 32 over 1. And so we can multiply that to the numerator, and then we now have this. Let's multiply 32 right here. Now notice that 32 and 2 will cancel. So this will become 16. And so reordering the equation, we have the maximum shearing stress will be P over pi d squared over 4 plus 16 pr over pi d cubed. Now we can actually move this term outside, and then let's try to derive a formula. However, you can just actually memorize this formula so that you will not memorize any new equations. However, just for the purpose of efficiency, to solve problems in helical springs much faster, let's just derive a formula. But it's actually better to just memorize this. But for now, let's just derive the equation. We can move this outside, and then we have the maximum shearing stress is equal to 16 pr over pi d cubed. Now how are we going to get the first term? We actually need to divide this term by this term. Now recall again that when dividing something by a fraction, you can just simply multiply the two terms, but you will need to take the reciprocal of what we are dividing by. So just for clarity, if let's say we have 1/4 divided by 2/3, this will become 1/4 multiplied by 3 over 2, because this is the reciprocal of what we are dividing by. And so if we'll divide this by this term, we need to get the reciprocal of this term. So we have p over pi d squared over 4 multiplied by the reciprocal of 16 pr over pi d cubed. So that's pi d cubed over 16 pr. Now in here, d cubed and d squared will cancel, p will also cancel, pi will cancel, and then 16 over 4 will also cancel. So we have, this will now become d, and then 16 divided by 4 will be 4. So this is 4, and then p will cancel, pi will also cancel. So we have d over 4r. And so for the first term, we have d over 4r. And then since this term and this term are just similar, then we can just say that this is plus 1. Or simply, if we'll divide this term by this term, the result will be 1. And so we now have this formula. And so let's move that here. Now take note that this formula neglects the curvature of the spring, and it is only used when d over 4r is very small. And so these are the conditions that you have to remember. However, for heavy springs and considering the curvature of the spring, we'll actually use A.M. Wahl's formula. in which the maximum shearing stress will be obtained using this formula. We have 16 PR over pi d cubed multiplied by 4m minus 1 over 4m minus 4 plus 0.615 over m. Now this is an empirical formula, so we will not be deriving that. However, just try to memorize the formula. Now this expression, this is called the Wahl factor. And then by the way, m right here, this is the ratio of the mean diameter to the wire diameter. So m equals the mean diameter over the wire diameter. Or that's simply capital D over D as labeled right here. However, since in most cases, we are given the mean radius, we can also define m as 2r over d. Now this is just capital D. And so since we are done with shearing stresses, we will now move on to the deformation of helical springs. Now if we'll apply a force P right here, then this will naturally cause the deformation of our helical spring. And so applying the force P, the spring will actually elongate because we are trying to stretch it. So this is now the movement. Now, this was the original configuration of the spring, these transparent parts. And so this is actually the movement of the spring. And so if we are just to consider this movement, this will be equal to the individual movements of the coils above. Now, our formula for this movement is defined by 64 PR cubed n over GD to the fourth. So we have this formula, and then G, as you can recall, this is the modulus of rigidity, or the shear modulus. And then N, in our formula, is the number of turns. By the way, this is considered one turn. This is another turn, and so on. And then R is the mean radius, P is the applied force, and then D is the wire diameter. Now we also have our spring constant, which is the ratio of P to the deformation. So that will be P divided by the deformation, and so the resulting unit will be Newton per mm. Now this is simply P divided by 64 PR cubed n over GD to the fourth. And so this will cancel, and then we are left with 1 over 64 R cubed n over GD to the fourth. Now we can just multiply the reciprocal of this term to the numerator. And so doing that, our formula for K will be GD to the fourth over 64 R cubed n, which is just the reciprocal of this. And so just to recap, we have these formulas. This is for the spring deformation, while this is our spring constant. And then for the maximum shear stress, we have neglecting curvature. This is our formula. And then using Wahl's formula, or considering curvature, we have this formula. Now we have two formulas for maximum shear stress, but for design purposes, we'll just actually use this formula. However, in some problems, if it is not mentioned that you need to use the Wahl's formula, then just use this. And so to reinforce what we have learned, let's try to solve this problem. Now we have a phosphor bronze spring that has an outside coil diameter of 218 mm, and then it consists of 25 turns of 18 mm diameter wires, and then the spring is subjected to a force P equivalent to 500 newtons. So we have a force P right here, which is 500 newtons. And then for letter A, since we have to calculate the maximum shearing stress neglecting spring curvature, we have to use this formula. So we have tau equals 16 PR over pi d cubed. So this is 16. And then our P is 500 newtons. So this is 500 newtons. And then our R is actually the mean radius. Now here, we are given the outside coil diameter. Now what is this dimension? The outside coil diameter is actually D sub O. So this is 218 mm. However, we need the mean radius, which is this dimension, or simply half of D. So we need to get D first. Now to get D, since we have the outer diameter, this will actually be DO minus, this is the center of the wire. And so half of this will be small letter d divided by 2, and also here, d over 2. And so to solve d, we actually need to subtract d over 2 and d over 2. So this is the outer diameter minus d over 2 minus another d over 2. However, since we are subtracting this 2 times, we can just say that this is the outer diameter minus the wire diameter. Again, this comes from d over 2 plus d over 2, which is equal to d. And so this is now our formula. So to solve d, we have the outside coil diameter is 218. So this is 218 mm minus the diameter of the wire. So this is actually minus 18 mm. So our mean diameter will now be 200 mm, which comes from this equation. However, since we are talking about the mean radius, then we need to divide this by 2. Or simply, the mean radius is 100 mm, half of this value. So this is times 100, and then divided by pi times d cubed. This is the diameter of the wire, so we need to use 18. So this is 18 mm, and then cubed. and then we have d over 4r, in which our d is 18, and then over 4 times r, which is 100 mm. So times 100 mm, and then plus 1. And so this is now 16 times 500 times 100 over pi times 18 cubed multiplied by 18 over 4 times 100, and then plus 1, we have 45.63. So this is 45.63, and then our unit will be MPa. Now sir, why is this MPa? Notice that this will cancel, and then here, this will be mm cubed if we will cube this term. So this is essentially mm over mm cubed, which will give us mm squared at the denominator. So we have Newton per mm squared, that will be MPa. So this is now our answer for letter A. Now for letter B, we need to calculate the maximum shearing stress using the Wahl correction factor. And so we will now use this formula. Now again, this was 218 mm, and then our D was 200 mm, and our R was 100 mm. And so we need to first recall that M is equal to 2R over D, or simply D over D, in which this is the mean diameter, while this is the wire diameter. So this is now the mean diameter, which is 200 mm, over the wire diameter, which is lowercase d. This is 18 mm. So over 18, this is equal to 200 over 18. This is 100 over 9, or 11.11. However, to use the exact value, let's just store this into a variable. Let's say A. So M is now stored at A. So this is 100 over 9, which was stored into A. And so we now have the maximum shearing stress equal to 16 times P, which is 500 newtons, multiplied by R, which is 100 mm, over pi d cubed, which is pi times the wire diameter, 18 mm, and then cubed, and then times 4m minus 1, in which m was stored into A. So this is 4a minus 1 over 4a minus 4, and then we have plus 0.615 divided by A. So this is now equal to 16 times 500 times 100 over pi times 18 cubed multiplied by 4a minus 1 over 4m minus 4, and then plus 0.615 divided by m. And so this is 49.32. So we have 49.32 MPa, which is, as you can notice, larger than the result in letter A. So this is actually more conservative because this is assuming a larger stress for design purposes. And so this is another thing you have to remember. The maximum shearing stress using the Wahl correction factor will always be greater than the result of this formula. Now for the next problem, we will now solve the elongation of the helical spring. And so we will now be using this formula. So we have the deformation equals 64 multiplied by P, which was 500 newtons. By the way, this was 218, this is 200, this is 18 mm, and this is 100 mm. So 64 times P times R cubed. So this is 100 mm and then cube multiplied by n, which is the number of turns, which is for this problem 25. So times 25 divided by G, which is, by the way, since this is a bronze spring, our G is equal to 42 GPa. But this should actually be stated in the problem. And so using this shear modulus, we have 42 GPa, which is Newton per mm squared, multiplied by d to the 4, in which our d is the wire diameter, so 18 mm to the 4th. Now let's try to make sense of the units. At the denominator, mm squared will cancel, and then this will be mm squared from mm to the 4th, and then n will cancel, and then this will be mm cubed. So mm cubed over mm squared will give us a result of mm. So that's why this is our resulting unit. And so this value will be 64 times 500 times 100 cubed times 25 over 42. By the way, this was actually GPa. So we still need to convert this. So this is actually 42 GPa multiplied by 1000 to convert it into MPa. So 42 times 10 to the 3, and then multiplied by 18 to the power of 4. So this is now 181.447 mm. This is now our answer. Now for the last problem, we have to compute the spring constant. And so we will now be using this formula. So again, our G was 42 GPa. And so for the spring constant, we have K equals G, which is 42 GPa, which we will multiply by 1000 to convert it into MPa. So this is now MPa, which is n per mm squared, and then multiplied by d to the 4th, which is 18 mm to the 4th, and then over 64 times r cubed, which is 100 mm, and then cubed. multiplied by n, which is 25. So this is now 42 times 1000 times 18 to the 4th over 64 times 100 cubed times 25. This will give us 2.75562 or approximately 2.76. So this is now 2.76, and then our unit will be Newton per mm. Now for the cancellation of units, this will be mm squared, and then at the bottom we have mm cubed, and so mm squared over mm cubed, we have mm right here, and then for the numerator we have newtons, and so that's why this is Newton per mm. And so just an additional input, if you're given the spring constant and then you're given the deformation and you're asked to find the force, then you will just actually use this. For example, we know that the deformation earlier was 181.447, and then let's say you are given the spring constant and then you're to find the force. So to find the force, you have P is equal to the spring constant multiplied by the deformation. So to solve P, which was 500 newtons, we can multiply K and the deformation. And so let's just store this. Let's put it into B, and then B times the deformation, which is 181.447. We now have the force 500 newtons. And so this is also something you have to remember, because in most cases, we are actually given the spring constant.